I need your full attention because this is the most important session of our entire masterclass. In our last session, we built a strong foundation. We learned all about the automatic tetrahedron method. So what will you learn by the end of the session? First, you will understand what each of these four powerful methods on your screen does: hex dominant, sweep, multi-zone, and Cartesian. But much more importantly, you will learn the secret that separates a beginner from an expert. You will learn how to choose the correct method. By the end of this session, you will have a clear, simple guide. When you see a new geometry, you will know exactly which tool to use to get the best possible mesh. Hello everyone, welcome to session 5 of our ANSYS meshing course. As you remember, in the previous session, we started the mesh method in ANSYS meshing, and as you do remember, we started learning the tetrahedrons method that you can see right now is applied on a pipe geometry. As you can see through the mesh metrics down here, the minimum number of elements and also the element matrix show 0.27, which is not a great quality. We can also try using the orthogonal quality. And our main concern while using the mesh methods is increasing the quality, but also decreasing the computational load and time. So I should say we aim to learn why and how to apply hexagonal elements on our model. So there is a big question here: why we insist on using hexagonal cells in our model? This image gives us the perfect answer. Look at the two examples here. On the screen, we have the exact same geometry meshed in two different ways. First, look at the top one. This is a tetra mesh. It's made of tetrahedron elements. To mesh this object, the software needed about 48,000 cells. Now look at the bottom one. This is a hex mesh. I mean, it's made of hexahedron cells. To mesh the same object, the software only needed 19,000 cells. This is a huge difference indeed. The hex mesh used less than half the number of elements. So this brings us to the two most important reasons why we always prefer a hex mesh. First, it makes our simulation faster. Fewer elements mean the computer has less work to do. And second, it gives us more accurate results. This is very important for CFD simulations in Fluent. With a hex mesh, the elements are often structured and organized. We can align them with the direction of the fluid flow. So when the mesh lines follow the flow, the solver can calculate the physics more easily and with less error. This means we get a reduced numerical error and more reliable, accurate solution. So to summarize, we always try to create a hex mesh because it is more efficient. It gives us a faster simulation with fewer elements and a more accurate results. Well, so I guess right now you actually notice why I put emphasis on this current session. Because in the previous session, we used tetrahedron's mesh method, which somehow avoids generation of hexagonal cells, which is a prior choice. So we're gonna explain the other methods, starting with hex dominant and then continued by strip, multi-zone, and Cartesian methods. But of course, you need to know either of them and how to use them and apply them on your own geometry. Otherwise, you cannot wisely choose them. And this brings you many errors during the simulation regarding the convergence or divergence issue and some other problems. So let's start from the hex dominant. I want to start with a big question. How does it work? It first makes a quad mesh on the outer surfaces, so it is two-dimensional first. Then it pushes this mesh inside a little. The empty space left in the middle is then filled with other elements such as pyramids and tetrahedrons. This is why it is called hex dominant, not a pure hex mesh. It's important to note that this method might not be ideal for some CFD simulations, and it cannot be a prior choice, and you will notice why I'm saying this. Let me get back to our model, the pipe, and let's just change the method to hex dominant this time. So, as always, it starts with the element order that we learned in the tetrahedron. No actually difference. But we have another choice in here, which is called free face measurement type. This option controls the shape of the elements on the outside surfaces of our model. Because as I mentioned, in the initial step, this hex dominant method gonna generate a surface mesh on the surfaces of our model. And by applying free face mesh method, we are somehow applying this. So we have first the quad or a tri option. This is the default. It means ANSYS will try to use quads for sided elements. But if it's difficult, it will use some triangles to make the mesh fit well. This is usually a flexible and safe choice, but we have all quad option as well. This forces ANSYS to only use quadrilateral elements on the surface. This can give a very clean and structured surface mesh, but for very complex surfaces, it can sometimes create lower quality elements because it is less freedom. So I wanna employ, and let's just examine the quad or triangle cells on the same pipe that we gonna investigate and explore different mesh methods. Very well. So as you can see, we have a great mesh using hexagonal cells, as can be seen from the outside view. But the point is that as you check the quality regarding the orthogonal quality, you can see what's going inside. As pointed out and shown in here, we have the minimum orthogonal quality of 0, which is a poor mesh, and it just somehow guarantee that. Because it's not only the hexagonal cells. As you pointed out, it's just hex dominant, and it will allow the software to generate the pyramids, wedges, and also tetrahedron elements. So maybe it's better to actually create a section plane exactly in the middle. And right now you can see what's going inside. And this is actually the main and major reason that we try to avoid hex dominant method when it comes to CFD simulations. So I should say that in all, or better say most of the CFD simulations, we avoid using this method. But this method is not good for the cases that you need pure hex mesh or you need CFD accuracy. But it could be a great option when none of the other mesh method works. And for example, we better use the sweep or multi-zone methods. But if they do not work, we can get back to hex dominant method. So it is not what we aim to do, and it cannot be our prior choice always. But by end of the session, we will learn when to use it. So for now, we should say we remove hex dominant from a mind because it cannot be helpful. So our next method that is proposed by the software is the sweep method. Of course, you may heard of it in different softwares and you already know how it works, but let's just check it out. So as you can see in this slide, the idea is very simple. First, ANSYS creates a beautiful 2D mesh on a starting phase. We call this the source. Then it pushes or sweeps that 2D mesh all the way through the body to an ending phase. We call this the target. And this creates perfect layers of brick shape like hexagonal elements. Because we have fewer higher quality elements, our simulation will be faster and more accurate. So the most important rule is that, is the body sweepable? The sweep method has one very important rule. It only works on sweepable bodies. So the big question here is that how we can detect that our model is sweepable or not. If you right click on the mesh, you would see that through the show tab, we have sweepable bodies. After selecting that, the software will show you and color the model at, actually better to say, the sweepable bodies in the green color. So by doing so, we can detect if our model is sweepable or not. So when the model is sweepable, we can say sweep mesh method is the best choice, and we can actually create the high quality grid, mostly hexagonal cells, by applying this. So let's just check the details pane. And as always, we need some details and some options regarding each of the models. So first it comes the source or target selection. As I pointed out, this mesh will be started from the source and ended will be the target face. So by default, the software uses automatic tool, which ANSYS will try to find the start and end faces by itself. For simple shape, this works well. But when it comes to some more complex geometries, this method may not be a great choice. In these cases, we'd better use manual source or manual source and target. By applying this, the software will ask for the source, I mean the starting phase, and also the target phase. But for the pipe that we already investigating, maybe the automatic choice would be perfect. We also have another option that is very important here, and it is the strip number of divisions. That is default right now. But if you click on that, you can define the number of divisions that you want. So this is very simple setting. It asks how many layers of elements do you want along the sweep path. If you enter, for example, 20, the software will get 20 layers of elements from the source to the target. We can just check it. Let's just generate the initial grid using sweep method. And here we go with the mesh. As you can see, it automatically detected the source and also the target face. And during this path, it applied 20 number of divisions. One more important thing is that, as you can see within the mesh metric box, the minimum orthogonal quality is above 0.6, which is great actually, because it guarantee the quality of our grid. And if you remember the hex dominant, it was very poor, and this is the main reason we try to avoid it. So we have some other options here that may be helpful, such as the free face mesh type. Once again, as the title suggests, and we explained in the previous method, it just asks for the type of elements that it's gonna apply on the source initially. So maybe the quad or tri would be the perfect option, because the software will try to choose and generate hex or quad cells on the 2D face and then move it along the path. So this is all we need to know about the sweep method. And don't forget that it is a prior options in most of the cases. And the reason is actually evident. We explained that. So we have another option after strip, and it is the Cartesian that you can see beneath the multi-zone. So how it works? This is actually a very unique technique. This method thinks about meshing in a completely different way. The Cartesian method does not start from the surface of the geometry. Instead, it builds a large structured grid of hexahedral elements, perfectly aligned with the x, y, and z coordinate system. Then it fits this grid to your geometry. It is a body-fitted mesh. This method is excellent when your model has many features that are already aligned with the X, Y, and Z axis, like electronic components or some process industry equipment. It is also the recommended method for additive manufacturing simulations. So as we go through the details, you can see in ANSYS meshing that we have access to some options as always, and we can start by the element size. This is the simple choice. You just enter one value and ANSYS will try to create cubes of that size everywhere, but it does not guarantee that. And also, we have the number of divisions if we want to choose that uh, for the child. And by doing so, I mean by picking the number of divisions, this is different. Here you tell ANSYS how many elements layers to create in Z direction. ANSYS then uses that to calculate nominal size, which is also applied to the X and Y direction. But we have the scale advanced option down here, which is somehow the specification of the Cartesian, or better say body-fitted Cartesian method. So as you can see, It starts with the spacing option, which is by default on uniform. But we have some other options to capture the features. For example, uniform is the basic option. It just creates an evenly spaced grid. This is fab, but it might miss small features or create distorted elements near corners. And then it comes the key points, although this is a smart option as it automatically finds the important corners on your model and creates grid lines that pass directly through them. This helps the mesh respect your geometry's feature much better. And finally, the key points manual. As the title suggests, this gives you full control. You can manually select the vertices that you want the grid lines to pass through. So let's just keep on with the uniform. And within the advanced box, you would see that this is where the real power of Cartesian method is. The projection factor comes first. This is the most important setting to understand. It is number between 0 to 1 that controls the balance between mesh quality and geometry accuracy. So think of it like this. A projection factor of 0 gives you beautiful, perfect hexagon elements everywhere. But the surface of your mesh will look like a stairs. We can just try it, it will just act like stairs. And as you can see in here, it completely changed the model and couldn't detect the features. We have curve around the, let's say, pipe, and by using this projection factor of 0, we somehow avoiding and denying that. So the default value of 1 or 0.98 does the opposite. It forces the mesh nodes to sit exactly on the real geometry surface. So let's just try it once again. And now it just made it worse. So let's see what has changed in here. First of all, we forget to turn back to element size to detect smaller elements. And right now, I guess we can have the full curve and cover the full pipe. So right now, you can see it just did the opposite and tried to put all the initial cells on the surface of our pipe. So for additive manufacturing, the default is 0, which is what we need for the type of simulation. Then it comes a stretch factor along X, Y, and Z. This is a great tool to reduce the total number of elements. If your part is very long in one direction, such as our current model, which is long through the Z direction, you don't need perfect cubes. You can set the stretch factor in Z to 3, for example, and this allows the elements to be 3 times longer in the Z direction than they are in X and Y. So let's see what happens. We expect longer elements through Z direction right now, and it's completely true. We can say it successfully applied. So let's get back to 1. I want to point out one more important thing, and it was about the quality. As you can see in here, the element quality regarding orthogonal quality somehow exceeds 0.6 again, such as what we saw with the sweep method, but not the hex dominant method. So I should summarize. The Cartesian method is a very robust and powerful tool for creating pure hex mesh, especially for models with features aligned to the coordinate system, or for additive manufacturing. Your main job is to balance the projection factor here to get the mix of elements, quality, and surface accuracy that you need. So this can be another choice when it comes to hexagonal cells. And up to now, we can say our prior choice is strip and then Cartesian. We haven't investigated the multi-zone yet, but we are already aware of the poor quality of hex dominant. So as the very last method, we're going to explain and investigate the multi-zone method. So as our last method, we can look at one of the most intelligent and useful meshing method in ANSYS, multi-zone. The best way to think of multi-zone is an automatic smart sweep method. The regular sweep method only works on simple sweepable bodies, as you remember. But what if your body is too complex to sweep? That's where multi-zone comes in. it automatically decomposes or slices a complex body into multiple simpler blocks. Then it routes a high-quality hex mesh through each of these blocks and connect them all together. So I paused the video to import another geometry this time. And as you may notice right now, the difference between the current one and the previous pipe model was about the complexity of that. Of course, if we do not have these things on our micro channel, we can say this could be a simple sweepable body. But right now, if I just check the sweepable bodies, we cannot see any body colored in green. This shows that the sweep method cannot work again. So let's just generate and try using sweep method. And as you can see, we faced an error called measure failed to initialize. So from now on, we need to consider that if a model is much more complex than a simple sweepable body, we'd better use the multi-zone technique. This is somehow, as I said, like the intelligent version of the sweep method, and it automatically somehow slices this body into sweepable bodies. Because as you know, the microchannel itself could be a sweepable body, and also each of these things could be sweepable as well. So after selecting multi-zone, you can see some several options, starting with the mapped or stripped type. So this is the most important setting in multi-zone. It tells the measure what kind of elements you are willing to accept in your final mesh. So for your face choice, you can see the hexa. You are demanding a 100% pure hexahedral mesh. No other elements types are allowed. So let's just try it. The hexa cells as the results. This gives you the highest possible mesh quality for solvers. However, if multi-zone cannot find a way to slice the body perfectly into sweepable regions, the meshing process will fail. But right now, we didn't encounter with any issues and any failure. And as you can see, it automatically, without any further settings and specifications, could create a very fine grid, and the orthogonal quality shows the minimum value above 0.8. This is actually great because we couldn't do this using any other mesh method. So let's just check the other ones. For the backup plan, you may have the hexa or prism and also the prism. Of course, needless to say, these are just for the safety, because it tells ANSYS try your best to create a pure hex mesh, but if you can't, it's okay to fill the difficult parts with prisms or wedges elements. Or you can just simply use the pure prisms. So of course, our prior choice always would be the hexal mapped open swept type. Then we have another important thing, which is free mesh type, and by default, it is not allowed. So this parameter is directly connected to the one above. It only becomes active if multi-zone needs to create a free mesh. For example, when you use the hexagonal or prism. So it defines what element type to use in the non-sweepable leftover regions. So for now, we do not have any leftover regions, and we could successfully create that. For any complex object that you may have some leftover regions, this can help you. So by using not allowed, which is the default one, we somehow let's say allow hex elements and no other free mesh types are allowed because we selected hexa up here. But for other ones like the hexa or prism, we may better use other methods such as the tetra pyramids, the hex dominant, or hexacore. So let's just have a brief explanation. For Tetra, the leftover regions will be filled with standard tetrahedron elements. Next, it's the Tetra pyramid. This is often a better choice. The leftover regions are filled with tetrahedrons, but it automatically adds a layer of pyramid elements to create much better quality transition between the hex blocks and the tetrahedrons. And then the hex dominant, once again, or the hexacore, these are advanced algorithms that try to force hexahedral elements even into the free regions. They are more aggressive but can sometimes create lower quality elements in the process. For most cases, Tetra or Pyramid is the safer option. But for now, we could successfully create that using the hexa cells and we do not need them. And as I pointed out, the great feature or the powerful part of this multi-zone method is the automatic decomposition of it. But what if you cannot automatically find and slice the complex geometry? In these scenarios, you have several options such as thin strip, the card strip, and the standard. So your best choice always is the program control, which allows the software to automatically detect and decompose the object. But if it could not be successful, you can go on using the thin strip, which is a special algorithm optimized for slicing thin sheet-like bodies, and card strip tries to create the slices that are aligned with the global X, Y, or Z coordinate system. It's somehow useful for block geometries that are already aligned with the axis. And finally, the standard, a more general older algorithm, program control is usually smarter. So I should say that it goes without saying the multi-zone is the perfect choice when it comes to complex options, but only the strip method does not work. So as the very final step in this session, we need to learn when to use either of them. To summarize, I should say this is the most important slide in our masterclass. It answers the question you will ask every single project: which method should I use? So first, you always start with this special question. Is your geometry very dirty, meaning it has lots of small errors, gaps, or problems? Or are you doing simulation for additive manufacturing? If the answer is yes, your choice is simple. Use the Cartesian method. It is incredibly strong and robust, and it can handle bad geometry better than any other method. It almost never fails. Then, if your answer is no, you move down to the flowchart to our main workflow. The first question is always, is the body simple and can it be stripped? Think of a simple pipe or block or any shape that looks like it was made by extruding a 2D face. If yes, you must use the strip method. This is your number one, gold standard choice. It will give you a perfect pure hexahedral mesh that is the most accurate and efficient for the solver. Okay, what if your body is too complex for the strip method? The next question is it almost strippable? Does it look like it's made of several simple blocks joined together? If yes, you should use multi-zone. Think of multi-zone as the smart automatic version of strip. It will try its best to cut the body into simple blocks and give you the high-quality pure hex mesh you want. Now, if you even multi-zone cannot handle the geometry because it is just too complex, think of a car engine or a human artery. We have to use an unstructured method. For this very complex shape, our standard and most reliable choice is the Tetrahedron method. It is very flexible, can mesh almost any shape, and modern CFD solvers are excellent at working with high-quality Tet meshes. Finally, we come to our last option. What if you have tried everything else and it has all failed? You just need to get any mesh to see some preliminary results. Only then, as last resort, should you use the hex dominant method for CFD. Why is our last choice? Because while it creates hex elements, it can also create lower quality elements. We actually examined it during this session, and you're already aware of its drawbacks. So the strategy is clear. Always try to get a pure hex mesh first with strip or multi-zone. If you can't, use the reliable tetrahedron method and only use hex dominant if you're completely stuck.